Hello, folks. Okay, today we're going to talk about the carbon cycle, and this is super important. If climate change is caused by greenhouse gases and carbon is involved there, which it is, then it is just crucially important that we totally understand the carbon cycle. So here's our learning objectives for today. Know what forms carbon is found in, on, and around Earth. Know and apply the concepts of reservoirs and fluxes. Get the carbon cycle model into your head. Know the big reservoirs of carbon and the imbalanced fluxes. And be familiar with the evidence from the NOAA observatories that sniff CO2. Atmospheric carbon is rising. Why? How much? And so what? Okay, so later on, go back, review those things, make sure you got them. So let's talk about carbon. Carbon, an element, which you know from our little chemical thingy, matter and energy lecture. Carbon occurs in many different forms, many different compounds on Earth. Diamonds is one. Actually, diamonds is not a compound. It's a molecule, but not a compound, pure carbon. Doesn't really, there's not many of them, so that's the last time I'll talk about diamonds in this course, but I just thought I'd do that now. Limestone is a big one. Limestone contains a lot of carbon. Bicarbonate ion dissolved in water. Coal, oil, and natural gas contain a lot of carbon. Those are the fossil fuels. Methane is another one. I guess methane's a component of natural gas, but I like to single it out because it's important on its own. Carbon dioxide. Roast beef, potatoes, and salad contain carbon. And also brie, cheese, fish, ice cream, beer, potato chips, chimichangas, chili peppers, platanos, pasta, tequila, cinnamon, vanilla beans, rice, cornmeal. Food, biomass in general contains a lot of carbon. Okay, so that's why I say just biomass. So anything living is not solely composed of carbon, but a lot of it is. Okay, so how much carbon is where on Earth and how fast does it change from one state to another? Here's two concepts you need to know. The first one is the concept of a reservoir. That is the amount at a particular point in time. So at this moment in time on Earth, there is a reservoir of biomass, and that may remain constant over the years or it may change, but right now it's this much. Flux is a fancy four-letter word with an F and a U in it, which is the flow from one reservoir to another. So when you eat food, you're eating biomass and it's becoming biomass, but part of that carbon that's in that food that enters your body is going to leave your body as carbon dioxide and go out of the atmosphere. So all the carbon dioxide that leaves biomass and goes into the atmosphere, if you could sum it up, would be a flux. It would be the flow from one reservoir, biomass, into another, the atmosphere. Okay, so let's talk about the carbon reservoirs. What are they? The big ones. So let's see, in this diagram, which I got from the US Department of Energy, shows the major carbon reservoirs, and the numbers there are gigatons. How much is a gigaton? A whole lot. So let's start with the atmosphere. I don't care that this image shows pre-industrial. I guess right now it's different. Who cares? We don't care right now. The atmosphere has got 600. Vegetation, all the plant matter on Earth, has 610. Cool. That's kind of interesting. All the plant matter on Earth contains about as much carbon as the atmosphere. What did you think? If it were me, I would have thought there's a lot more carbon dioxide in the atmosphere, but it turns out there's actually, as a percent fraction, there's not that much carbon dioxide in the atmosphere. Most of it is nitrogen gas and other stuff. Okay, and look, they don't even talk about they don't even talk about insects or animals. Why did I think of insects first? Animals, insects are animals. Humans and elephants and stuff, negligible. We are negligible compared to the amount in vegetation. That's why it's not here. The soils contain between 2 and 3 times as much carbon as the standing vegetation. That's interesting. Who knew that soils had so much carbon in them? They do, particularly if you include the those frozen soils of permafrost in the Arctic tundra. There's a lot of carbon locked up in there. The ocean, see now there's two levels of the ocean. The upper mixed layer, 1,000. So the upper mixed layer, which is really a thin layer, has more carbon in it than the atmosphere. The deep ocean has much more than anybody. This is the hugest reservoir of all of carbon, 38,000 gigatons of carbon. Oops, I'm wrong. Actually, sediments and rocks have much more. There's lots of carbon locked up in rocks. Okay, so let's rank them. Okay, sediments and rocks number one, deep ocean number two, soils, then the upper level of the ocean, and then these guys are tied. Okay, so those are the reservoirs. How did someone go out there and weigh it all? No, that's a whole nother subject. How scientists come up with these numbers, it's by sampling. Sampling yields an estimate of the true number, and there's a confidence interval around that estimate. We're not going to go there in this class, but I think you should be curious about that. Sampling. How do they do that, and how confident are they in their sampling? Scientists think about that a lot, but for this class, we're not going to talk about it much. Okay, now we're going to talk about the fluxes. So where did I get this? Can't remember. I got this from a good source. I just can't remember where. Sorry. This shows the fluxes, the changes in gigatons, but that's not a correct statement. It's not in gigatons. It's in gigatons per year. Okay, so a flux is a change of a certain amount over a certain time. Okay. In this picture, just concern yourself with the arrows because those are the fluxes. The numbers in boxes are the reservoirs. And look, they don't match up. This says 600, this says 775. I don't care. Doesn't matter. We're just looking for the main concepts here. So the arrows are fluxes. So these guys figure respiration and photosynthesis. Those are opposite processes, and we're going to talk about them soon in my favorite lecture, one of my favorite lectures. I think deep time is my favorite lecture. My second favorite lecture is Equation of Life on Earth, which is coming up. So we'll talk about respiration and photosynthesis in detail then. For now, just know they're opposite processes. Respiration is giving off CO2 because of your metabolic processes, and photosynthesis is the taking in of carbon and turning it into biomass. And if you look at these two processes, they're almost equal. Okay, so the fluxes here, living action of pretty much takes as much carbon out of the atmosphere as it returns. There's a slight difference, not much. Okay, how about ocean? Look at this. There's an imbalance between carbon leaving the ocean and carbon entering the ocean. And that is because there are some creatures, which we'll talk about soon, which incorporate carbon dioxide into a carbonate, which is a stone, basically, a mineral, and that does not go off as carbon dioxide until something else happens. Instead, that becomes a deposit. And so carbon is taken out of the ocean and deposited in sediments. So we have these red arrows are imbalances in the flux. We have a net ocean uptake of 2.2. I guess they didn't give decimals here because when you subtract 90 from 92, you get 2, but they're saying 2.2. Okay, fine. What else do we have here? More red arrows. This is a little bit confusing. Net ecosystem exchange, I don't know what it is. Changing land use, I don't know. There's a flux here. One is, I actually kind of do know what this means. There's more to what goes on land than just respiration and photosynthesis. So that's what ecosystem exchange is. In the end, there is some carbon being taken out of the atmosphere because of it. You don't have to worry about it because I'm being unclear. Changing land use definitely does contribute to carbon going into the atmosphere, and that would be different things. One thing would be burning of forests or conversion of forests into pasture or cropland. Forests tend to take nitrogen out of the atmosphere, and when you remove them from doing that and convert it to some other use, you get a loss. Okay, and so these are small, But so we're going to skip lightly over them and focus here on this one. Fossil fuels and cement, 6 gigatons per year. Look at that number. That's an imbalance. That's carbon being taken from the ground and put into the atmosphere and not balanced by anything being put back. 6 per year. So comparing to all these others, that's a big number. It's the biggest number here. So what I've done in the next slide is taken these changes, these imbalances in the fluxes, and added them up. And here's what I got. Okay, for the reservoirs, let's see. Oh, no, I'm sorry. In a future slide, I'm going to do that. For now, I just wanted to just list the reservoirs instead of previously we had them in a cartoon model. I just want to list them here in text for you to study. So our big reservoirs are the atmosphere, and this is carbon reservoir. So CO2 and CH4 both are compounds containing carbon, and so that is an atmospheric reservoir. Then there's the lithosphere, which means the stone or earth itself. So we have fossil deposits, fossil deposits, we'll think of them as fossil fuels, okay? And then limestone, which is also actually a kind of a fossil. So we have different kinds of carbon locked up in the stone. We have fossil fuels and limestone, which I'll say more about later. Then in the ocean, so we've got the atmosphere, the rock on the earth, and the ocean, and then we have the biosphere. So in the biosphere, we've got land plants, we have marine algae that are in the ocean, and we have consumers and soil biota. Okay, you don't actually have to know all these guys. Just know that the biosphere represents a reservoir. Okay, let's list the fluxes. The fluxes include photosynthesis and respiration, deforestation, ocean exchange. That's simply carbon dioxide being absorbed and also being given off by the ocean water. And then there's volcanic activity, weathering, and burial. And I list these things, I think of these things all the same way because really they are all what happens with stone. So volcanic activity can release a lot of carbon dioxide, but it's getting it from the earth. So there's rock down there that is outgassing and going into the atmospheric reservoir. So that's a flux. Weathering, I'll talk more about soon. And then burial of biomass is how carbon dioxide leaves the atmosphere, enters the biosphere, and then enters the lithosphere. So that's called lithification, and that's a flux. Another flux is the kind of the opposite of burial. It's fossil fuel combustion, where we take this fossil stuff that is lithified and then return it to the atmosphere as carbon dioxide when we burn it. Okay, those are all fluxes. I think that's all. Yeah, just wanted to say a little bit more about rock. Okay, so this picture is of the White Cliffs of Dover. They're in England somewhere. And the White Cliffs of Dover are composed of chalk, and chalk is composed of innumerable little tiny bits of single-celled algae called coccolithophores. So I don't know what a coccolithophore is. It's some kind of marine phytoplankton alga. And here's what they look like under the scanning electron microscope. They're beautiful and cute and tiny. And they're very tiny, but there's a lot of them. And they make up somewhere between 1 to 10% of all the carbon fixed every year in the ocean. So they're actually pretty important. 1 to 10% is a pretty large fraction given all the different photosynthetic organisms that are out there. So a lot of the photosynthesis that's happening in the ocean is being done by these guys. So they're taking CO2 out of the atmosphere and locking it up in these carbonate skeletons they have. And when they die, some of these guys just drift. When they die, they drift down and they accumulate as like a dusty deposit or sludgy deposit on the bottom of the ocean. And you wouldn't think that would matter much because even though there's a lot of them, they're really tiny, but it's thought that they accumulate where they accumulate at about a rate of 1 millimeter per year. 1 millimeter per year. How much is that? Well, you should know, actually. As I mentioned before, it's about the thickness of your fingernail. So that's a tiny bit, right? Yeah, it is. But now you have to realize that they've been doing this for a long time, millions and millions of years. So how much would accumulate over millions and millions of years? I did the math for you just to be a nice guy. All right, in 1,000 years, you'd get 1,000 millimeters. Okay, how much is that? Well, that's about a meter. That is a meter. And a meter, for those of us who are metrically challenged, is 3 feet. Okay, 3 feet of this stuff in 1,000 years. Okay, actually, it still doesn't seem like much. But keep going. Remember, there's a lot of time out there. In 1,000,000 years, that's 3,000 feet. Okay, now we're talking a mountain. Okay, the mountains to the east of us here are 3, 4, maybe 5,000 feet. So we're talking a mountain worth accumulating in 1,000,000 years. Well, 1,000,000 years, I mean, that's never going to happen. I beg to differ. Do you remember this slide? This is the timeline stuff. Since the dinosaurs, there have been 65 million years. Okay, so over that time, 65 times 3,000 feet, that's a lot. Okay, the point is that tiny little bits of deposition over long periods of time can really add up. So why haven't these coccolithophores taken all the carbon out of the atmosphere and stuck it in the ground? Because it slowly returns via weathering and volcanic action, which we'll talk about. Okay, so I think this is Mammoth Hot Springs in Yellowstone, and it shows a travertine forming, and these are hot springs, and really hot water dissolves limestone, and then when the water cools off at the surface, it deposits the limestone. So travertine is just redeposited limestone. Isn't that pretty? It's just kind of cool to see another place where carbon dioxide is in the lithosphere. I like carbonates. Here's another carbonate. This is marble. It's made from travertine, really, and well, that's not quite right, but close enough. It's a carbonate, and this is funny because I googled. I couldn't remember who did this. Was it Da Vinci or Michelangelo? So I googled Da Vinci Madonna statue or mother and child statue, and up came Michelangelo's Pietà. And so here it is. It's just, can you believe you can take rock and make something so beautiful? Well, you can. And now you know it's made of travertine. By the way, I think the stone behind it is also kind of travertine. Anyway, carbon, it used to be in the atmosphere, and then it was lithified, and then we hauled it up and turned it into something so beautiful and temporary. Oh, but look what happens when you put this stuff outside anymore. Acid rain can dissolve this lithified carbon. It can dissolve this limestone. I'm not going to do it up here. Here's a link to Tina Turner's song, I Can't Stand the Rain. So you can watch that, listen to that on yourself. And next time you listen to it, which you should listen to it soon, you can think of this poor faceless statue and know that her marble face is now floating around in the atmosphere in the form of carbon dioxide. Well, how does that form? Well, you don't have to know this stuff, but just in case you're interested in this chemical reaction, I like it. It's something that as a human being you run into a lot because you bake with carbonate, sodium bicarbonate, and you make carbon dioxide to make your bread rise and your cakes rise and your biscuits rise and your beer bubbly and your soda pop and so forth. And plus your tombstone, if you make it out of marble, is going to look like this in not too long. Why? Because of this reaction. So I'm going to just take 2 minutes to run you through this. Here's a chemical formula for limestone. H plus is acid. So if the water that falls on limestone is acidic, and it is naturally and also because humans pollute it, then what happens is that the acid attacks it, pulls off this calcium part of the compound, and leaves behind this HCO3, which is the bicarbonate ion. This then reacts with more acid, which is present, and temporarily forms this funny thing, and then turns into this, which is water and carbon dioxide gas. So from a user's point of view, limestone and acid, either vinegar or acid rain, is going to give off carbon dioxide and water. Okay, so again, that's above and beyond your requirement to know for this class, but you might be interested. Also, know that a lot of the carbon dioxide that goes into the atmosphere gets absorbed by the ocean, and which is great because if it didn't do that, the climate change and global warming would be happening much faster than it is. So it's great that the ocean is absorbing this stuff, but when it does, it gives off this, and so it makes the ocean a little bit more acidic than it was. And ocean acidification is becoming an increasing concern because the clams and the mussels and the barnacles and the coccolithophores, which are taking that carbon out of the atmosphere and locking it away into those deposits, may be having trouble doing that when the ocean's acidity gets too high. So is that climate change? Not really, but it sure is related to climate change. So that's why I raised it at this point. You'll hear about ocean acidification if you read the newspaper. Okay, so here's a question. The carbon cycle, is it in steady state equilibrium? What do I mean by that? Are the inputs equal to the outputs in all of the reservoirs? Is it? No. But what happens if the inputs don't equal the outputs? Well, just think about it. Let's take the atmospheric reservoir. If there's more going this way than is going this way, then this is going to increase. Okay, I hope that's obvious. It seems obvious to me. If it's not, think about it. Get back to me if you have a problem. Okay, so if inputs don't equal outputs, then the reservoir will change. Okay, that's funny. Oh yeah. Okay, yeah, so here's where I did the addition for you. I added up atmospheric carbon flux from this model. If I forget to say this later, I'll say it now. This model is just a figure I pulled off the internet. I don't really trust it that much. It doesn't matter for the purposes of us. We don't really need it to be perfect. I'm just trying to illustrate a point. Now, if you wanted true values for these, you're never going to get them because no one can measure the true value of these things. The best scientists can do is make measurements and estimate these fluxes and these reservoirs. And they do that, and they're very critical of each other. Many people contribute to coming up with a good model of the atmosphere and the carbon budget. And it changes from year to year with better measuring systems. But just sort of at some point, we've got to trust the scientists to do their best, but know that future changes in technique or theory may change this model. Okay, so anyway, I'm going through the exercise of doing this. So the fluxes in according to that were 1.3 plus 2.2 plus 1.7. That's 5.2. That's how much carbon is coming out of the atmosphere through the various processes we mentioned before. Here is the flux into the atmosphere, 1.4 and 0.6. So 7.4 gigatons per year are going into the atmosphere, 5.2 are coming out. If you subtract 5.2 from 7.4, you get 2.2 gigatons of carbon added per year. That's what that model says, okay? But you must be a good critical thinker. Claims such as, hey, we're pouring 2.2 gigatons per year into the atmosphere must be backed by evidence. This is a calculation based on a phony model. But what is the evidence that this is actually happening? Great, we actually have it. I'll just read the text. The model suggests that the carbon input into the atmosphere is greater than the output. What is the evidence that this is actually happening? Good question. I'm glad you asked it. Oops, my timer didn't go off. Rats, because it was a funny one. It was the gummy bear one. But so take a break. And then we'll come back to this. I'm back. Okay, so what is the evidence? Is there any evidence? Yes, that actually carbon dioxide is rising in the atmosphere. So here are our friends, the National Oceanic and Atmospheric Administration. This is the U.S. federal government wealthiest nation on earth, I think, and they've got a great scientific arm here. They give us our weather reports, they put up satellites, they gather data, they make it publicly available, they hire people to study this stuff, and they put observatories in Alaska, Mauna Loa, the South Pole, and American Samoa to sniff out carbon dioxide, just to measure how much CO2 is in the air. Let's look at these places and ask ourselves why these locations. So I went to Google Earth. So let's see. First of all, Point Barrow is way far north. Why did they put it there? Because they couldn't put it on the North Pole because it's hard to do that because it melts and moves around and stuff because it's a frozen ocean. But there it is. Actually, you zoom all the way in, you can actually see their station. Here it is. They have a landing strip and stuff. I'm looking for a round building. Usually they have like a dome somewhere. Anyway, it doesn't matter. So there they are. They're sniffing the air way up north. The other one is on the South Pole. So they're on the South Pole, which is stable enough to have a station. And then the other ones are on Mauna Loa, which is in Hawaii, the island of Hawaii, the big one, which is, we're actually not going to zoom all the way in yet. Look where Mauna Loa is. It's in the middle of the Pacific, and it's quite close to the equator. It's like 15 degrees north. And we will zoom on this one because I think they do have a dome. You can zoom right in, right? Oh, by the way, the prevailing winds are in this direction here. So they're sniffing really well mixed atmospheric air. Okay. And zooming in, hope you guys can see this. I think you can. Right on top of this volcano. They're not sniffing the volcano though, I don't think. So that looks like a lonely place, but that's where it is. And the last one is in American Samoa. Where the heck is that? Just on the other side of the equator. So it's in the southern hemisphere, and they're actually over here in the north end of the island. And let's see, that is south. Ooh, yeah, they're 14 degrees south. So they're about equidistant from the equator, but to the south of Hawaii. Okay, so they're sniffing both sides of the equator. So we got the North Pole in Alaska, this close to the North Pole in Alaska. We've got the South Pole, and we've got here. So we've got a pretty good sample of the Earth's atmosphere. Aren't these guys great? I think so. I'm just so excited that they do that stuff. Wait till you see their data. Okay, go here. Great. Okay. And this dude here, he's famous. Dr. Keeling, he started them. I guess he was in charge of this observatory for a long time. And he just, him and his team, they just set it up and they set up the protocols and they started measuring the atmosphere on a monthly basis. And they've been doing it for years and years and years. In fact, since 1950 something, 58, I think. And here's their data. Here are the years over here. Here's parts per million carbon dioxide at that observatory. The red line are monthly measurements, and the black line is, I think, is some annual averages. I think they're annual averages. Okay, and what do you see? It's going up. Okay, we knew it. You know what? I took a class here. I'll tell you more about it. I was a Humboldt State student in the mid 1980s, and I saw this graph then, right then, and I went like, "What?" Yeah, I'll talk more about that. And it hasn't changed since. It just keeps going up. In fact, it's going up faster than it was because we're just more people, more economic activity, burning more fossil fuels. Okay, so this was in 2012. Atmospheric CO2 has increased by about 20% since 1958. And just to be completely obvious and clear, you know what? I once heard of a book called How to Lie with Statistics. And one of the ways you lie with statistics or misrepresent data is by putting the x-axis not starting it at 0. Okay, so you could say, "Oh, what are they trying to lie with statistics or by not doing it at 0? No, not really. This is an important value. Since 1958, CO2 has increased by more than 20%. Okay, that's a big chunk of a greenhouse gas, no matter how you graph it out. Okay, we'll talk more about the seasonal cycle in a second, the up and down of that red bar. It's a seasonal cycle, and there's an explanation for it that it's fascinating. But I just wanted to close in on, let's see, 2008 to 2013. You see pretty much the same thing. The corrected value, I'm not sure what that is, mean, I think. Anyway, let's say just out of morbidity, I record this every year. The most recent time I recorded this was in March 2015. We're now, yay, at over 400 parts per million. That is a very sarcastic yay cheer. So that's what we're doing, folks. As a species, we are increasing the Earth's concentration of CO2. And we've done it more than 20%, and it keeps going up. This is not good. Okay, so what's up with the seasonality of the carbon cycle? Now, you could figure this out for yourself. This is what I did. Google seasonal CO2 fluctuations Y, and you can select this link. There you have a really good explanation, or I'll just tell you. What happens is, let's see, let's look at this. Okay, before I explain it, look at this. This is the 4 stations and their reports since the 1970s up to the year 2000. And the ones, let's see, that are red and blue, which are Samoa and the South Pole, are pretty constant. So what does Samoa and the South Pole have in common? They have their location south of the equator. Mauna Loa and Barrow are north of the equator. So there seems to be something different about the north hemisphere and the south hemisphere. And the thing that's different about them is that the northern hemisphere has a lot of land in it. If you take a look at the globe, and we're going to flip it to the South Pole, you don't see a whole lot of land here. Not much land where photosynthesis can take place. But if you go to the North Pole, there's a lot of land in the northern hemisphere. Okay? And so during summertime, there's a whole lot of carbon dioxide, and there's a whole lot of photosynthesis and respiration going on. Okay, in the southern hemisphere, not so much. And so in wintertime, the whole life kind of on the planet sort of shuts down. Sort of, doesn't really, but it reduces, and in summertime, it picks up. So I'm not exactly sure why during summertime CO2 would go up or down, but anyway, it doesn't matter. That's what goes on. That's the difference between the North and the South Pole. Okay? So that should be interesting to you. I hope so. It's interesting to me. Let's go back to our show here. What are we trying to say? Basically, atmospheric carbon dioxide going up because of fossil fuel use. And that's this stuff. The sources of atmospheric carbon dioxide increase mostly is because of fossil fuel combustion and a little bit of cement production. And in this graph, we've got 3 different kinds of fossil fuel uses graphed out since the 1800s, and cement is down here really small. This is the total. This is petroleum. This is coal. So petroleum and coal, they're starting to, I think, coal might be coming back and petroleum might be going down since 2000. I'm not sure. And certainly natural gas is going way up with because of fracking. Okay, and so that's where that flux imbalance is coming from, and that's why the atmospheric reservoir is going up about 20%. Okay. So, next question. Does this anthropogenic change in atmospheric carbon in the form of CO2 have an effect on climate? So I'm being very careful in my language here, and I expect you to be also. The change in atmospheric C is definitely anthropogenic. It's coming from the burning of fossil fuels and a little bit of cement. Okay? Humans do that. Antelope and nematodes are not doing that. Humans are doing that. And it's also not because of any Milankovitch cycle or sunspot activity or volcanic activity. The change, the 20% change, is due to human activity. So, is that having an effect on climate? Well, we know that the climate has changed in the ancient past, so there's no reason to say that it can't change again. Okay, we have precedent for climate change. And we know that CO2 is a greenhouse gas, so it makes sense that global average temperatures should go up as CO2 goes up. But we knew all this in the 1980s, okay? That was 30, almost 40 years ago now. But one must not be too hasty. There are lots of other questions to answer before making conclusions. As I said, when I was an undergrad in the 1980s and I saw our knowledge of greenhouse gases has not changed at all, at least not the theory since then. And we knew that CO2 was going up then, and we knew that more it would go up since then. But back then, scientists are very conservative and slow to jump to conclusions. Here's an alternative hypothesis. You know what? We increase CO2, maybe the temperature is going to go up a bit, but that means that the atmosphere will hold more water. And that might mean that there's more cloud formation. Clouds have greater albedo. That means more light will be reflected and the Earth will cool again. So it's not clear to us at this time, 1980s, that this increase in CO2 will cause global warming. That's what they said back in the 1980s. And so that's just one example. I mean, scientists have to think very, very critical about things and make hypotheses and test them and have that replicated and attacked by other scientists in a global community before, as a group, they move towards a conclusion. It's very conservative, very careful, and very slow. Okay, so stay tuned to the next lecture where the link between human activities and climate change looks like scientists are coming to a conclusion on this subject. So, in summary, I bet you can't make a joke about carbon, can you? No? See? That's a joke, you get it. Okay. Carbon exists in many forms on Earth. Name them. What compounds can you find carbon in? Diamond. Try the bigger ones, the more important ones. Good luck. Do that. The amount of carbon in each form is a reservoir. What are the largest reservoirs? I'm not answering that for you. I already told you. Carbon changes its form. The rate at which it changes from one form to another is a flux. Name some fluxes. Reservoirs remain constant when the flux in equals the flux out. They change when the flux in does not equal the flux out. So name some important imbalances besides human producing carbon dioxide from burning of fossil fuels. That's the number one. Try going with number two and number three. Okay, the atmospheric reservoir of carbon is changing. Why? How do we know? And by how much? Okay, that has all to do with that graph of CO2 going up. Okay, and does this mean humans are causing global warming? Not by itself. Okay, we'll go over the rest later. Thanks much. Take care.